That's the good news.
Jetzt unsere, sag mal, Dauergäste, also die regelmäßigen Besucher unserer Konferenz, die kennen ja fast schon dieses Duo. Nein, die kennen das, nicht nur fast, die kennen das. Meistens haben wir auf unseren Konferenzen das Gespann Professor Nir Schaviv und Professor Henrik Svensmark, die aus gutem Grund, wie Sie auch gleich sehen, im Päckchen auftreten. Aber zuerst möchte ich vorstellen den ersten Referenten, Professor Dr. Nir Schaviv. Er ist ein israelisch-amerikanischer Physiker, der am Rucker Institute for Physics der Hebrew University Jerusalem lehrt. Nir Schaviv schloss 1990 am Israel Institute of Technology in Haifa seinen BA als Jahrgangsbester ab. 1994 erlangte er den Master of Science in Physik und 1996 seine Promotion. Innerhalb der Astrophysik wurde er besonders durch seine Arbeiten zur Eddington-Grenze bekannt und er zeigte, dass astrophysikalische Objekte heller erscheinen können, als die Eddington-Grenze vorgibt. Er konnte daher den Masseverlust bei Eta Carinae und Supernovae besser deuten. Seine Arbeiten über den möglichen Zusammenhang zwischen kosmischer Strahlung und dem Klima sowie den Spiralarmen der Milchstraße und den Eiszeiten sind auf große Resonanz in der wissenschaftlichen Literatur und auch in den allgemeinen Medien bekannt. Nir Schaviv, Nir, we're looking forward to your presentation. Thank you.
It's a great pleasure being here today. I'm very happy that this venue was found after it was changed. Otherwise, I would have found myself roaming Munich for 2 days, and all I had to do was drink beer. So I'm happy the conference is actually taking place. I'm going to, whoa, this looks a little bit strange. I'm going to talk about, why does it look this way? Is there, let me try. Maybe this is better? No. I have no idea. Doesn't work. This is very strange.
So, während Professor Schaviv hier noch mit der Technik, der Kommunikation, meine ich, zwischen den beiden Geräten, möchte ich nur noch 2 Sachen dazu ergänzen. Wir werden im Anschluss ja Professor Henrik Svensmark auch sprechen. Und just tell me when I have to shut up. Und das Interessante ist, dass die Arbeit, die beiden machen, ja, letztendlich auch in der Wissenschaftsförderung so unbeliebt ist, dass die Förderung, die Finanzierung der Forschung, will ich sagen, eingestellt wird, aber Professor Svensmark jetzt seit einiger Zeit keine Chance hatte, seine Forschung fortzuführen. Okay, Nir?
Okay.
Excellent.
Don't upgrade to the last Apple system. Anyway, I'm very happy to be here. I'm going to talk about the role that the sun is having on climate change. I think it's very important, and I want to discuss in particular why it affects the way we understand climate change over the 20th century. So what I'll go on is first of all, start with a standard picture of global warming. We have to understand what people are saying in order to understand what's wrong with it. And then I'll show you evidence that the sun has a large effect on climate. that we can quantify it. We can understand how much the sun is affecting the climate, and we'll see that it's much more than just changes in the total solar irradiance. There must be another mechanism which is affecting the climate, that is, of course, the effect that cosmic rays have. And this I will leave for Henrik, who will talk after me over there. He will talk after me and describe the evidence for this link. But in fact, we don't really need to know what this mechanism is, because we already see quantitatively what are the effects that the sun has. And then we'll talk about what does it imply to changes in the 20th century and 21st century. So this is the standard picture that we hear every day from the IPCC. Basically, humans have increased the amount of CO2 in the atmosphere. That's one thing. The second thing is that CO2 changes the energy budget. The estimate that the IPCC uses is that we roughly increase the climate energy budget by about 3.7 watts per square meters if we double the amount of CO2. And then the critical thing is that how do we translate these changes in the energy budget to changes in the temperature, and that's the climate sensitivity. And if, for example, we use the CMIP models, whether it's CMIP 5 or 6, then we typically have some kind of sensitivity that this models gives, and this sensitivity is relatively large, so that if you take into account the fact that CO2 increased in the atmosphere, that CO2 changes the energy budget, and that it increases, these changes in the energy budget change the temperature, we expect that temperature over the 20th century should have increased. That's called global warming. And indeed, we observe that the temperature has increased over the 20th century. That's the standard picture. Now, if climate sensitivity is large, then it means that any future increase in the CO2 over the 21st century, if, for example, we go in a business-as-usual scenario and, for example, double the amount of CO2 over the 21st century, then the temperature will increase by a lot because climate sensitivity is high, and if the temperature is going to increase by a lot, then we are headed for a catastrophe. So this is the standard picture that we hear, and which is summarized by the IPCC reports every 6 years or so. And what is the evidence to support this picture? So first of all, did we increase the amount of CO2 in the atmosphere? Yes, we did. We know that because we can look at the isotopic composition of the carbon in the carbon-14 in the atmosphere until the 1940s and see that the amount of carbon-14 in the atmosphere decreased. And the reason is that when we burn fossil fuels, we burn fuel that was sitting in the ground for millions of years, so all the carbon-14 just decayed away. So when we burn fossil fuels, we decrease the amount of carbon-14 in the atmosphere. Now, from the 1940s, we don't see this effect anymore, but that's because we exploded nuclear explosions in the atmosphere, and these generate carbon-14, so we offsetted it. Okay, so we know we increased the amount of CO2 in the atmosphere. Now, do we change the energy budget? Well, there are calculations that give us, for example, this 3.7, give or take, watts per square meter if we double the amount of CO2. And there are some indirect measurements that show you that indeed there is such an effect on the energy budget, but they're not perfect. They're not. You cannot really measure this 3.7 watts, so that's why I gave it an imperfect check mark. Another problem, of course, is the warming. We have heard in this conference problems with the urban heat island affecting the temperature measurements and so on. So we know that the temperature has increased, but we don't know exactly by how much. If the urban heat island effect, for example, contaminates the land surface data and the land warming is only half as much, then it means that we should reduce the global temperature increase by about 1/6. So again, there is a check mark, but it's not perfect. The real problem with the standard scenario, the main caveat, is the fact that we really don't know what climate sensitivity is. What is the value of the climate sensitivity? If you open the IPCC reports, they tell you, as we heard a few times before, that the climate sensitivity should be anywhere between 1.5 to 4.5 degree increase if you double the amount of CO2. So basically, this picture is imperfect in the sense that if we, for example, sat in a closed room without being able to measure anything going outside, we wouldn't be able to predict by how much the temperature over the 20th century should have actually increased. We don't have models which can actually do that. Now, it's really interesting to understand why models cannot predict temperature change. We've seen one example in the previous lecture, but let's see where I think is the main problem, the main Achilles heel of the models. So, what is the greenhouse effect? We have radiation coming from the sun. Some of it is immediately reflected back to space. Some of it reaches the surface and reflected. But most of it is absorbed by the climate system, and then it has to be radiated away. The thing is that the atmosphere is opaque to infrared, mostly because of water vapor. Any molecule which is triatomic or larger, or has more than 3 atoms, absorbs in the infrared. And the most abundant triatomic molecule is, of course, that of water. So the atmosphere is opaque, and that means that instead of being at equilibrium at the surface with the amount of radiation that we get from the sun, the surface which emits the infrared radiation back to space is where the atmosphere becomes transparent, which is depends on the frequency around 10, 15 kilometers. What that means is that we have to advect the energy from the surface to that level somehow. It could be through radiation or through convection. But because we need to advect this energy, it means that the temperature at the surface has to be higher so that we can push this heat from the surface upwards. As a consequence, the temperature at the surface is higher than the equilibrium temperature at this level of, say, 10 or 15 kilometers. And therefore, it's warmer at the surface. This is the greenhouse effect. Now, what happens if we add another gas, like more CO2 in the atmosphere? The atmosphere is more opaque, and it's harder for the atmosphere to radiate this energy away. One way, so basically what happens is that all things the same, we reduce the amount of radiation that is emitted back to space. Okay, so we're not in equilibrium anymore. So what will happen is that the surface temperature has to increase in order to be able to drive this heat upwards. So we increase the temperature to reach back an equilibrium. Now, if everything would have stayed the same, a 3.7 watts per square meter change in the energy budget would have corresponded to about 1.2 degree increase. So without changing anything else in the atmosphere, doubling the amount of CO2 should have increased the temperature by 1.2 degrees. However, life is more complicated. When we heat the surface, we cause more water vapor to evaporate. So we have more greenhouse gas in the atmosphere, which wants to amplify it. On the other hand, if we have more water vapor in the atmosphere, we have more clouds. And it turns out that the clouds can change the energy budget by quite a lot. And it also turns out that we don't know by how much the cloud cover is going to change. So one of the main differences between different climate models is the recipe that they use in order to describe the change in the cloud cover. And one recipe will give you one sensitivity, and another recipe will give you another sensitivity. So the recipe you choose in order to describe the cloud cover will basically give you what is the climate model sensitivity. So climate models work in computers, it's called GIGO. It's garbage in, garbage out. Okay, I don't know how it translates to German. So because of that, different climate models have a wide range of climate sensitivities, which, as was mentioned before, is higher than what they actually claim is the range of climate sensitivities. To see that cloud cover are very important, we can go back to this graph from 89 and look at the range of climate sensitivities. You can see the climate sensitivity on the right axis as a function of the intrinsic feedback through cloud covers that you have in the models. At the x-axis, you see by how much does the energy budget change through changes in the cloud cover when we change the temperature. And you see that basically this is the most important parameter affecting the feedback of the climate system. If there is more feedback to the clouds, we'll get a lower climate sensitivity. If we have less feedback from the clouds, we'll have a higher climate sensitivity. This is the knob, which is artificially changed by the climate modelers, which govern the climate sensitivity of the models. Okay, so given that we don't know by how much the cloud cover changes when we change the amount of the temperature or the amount of water vapor, we cannot use climate models in order to predict by how much the temperature is going to change. Okay, so basically there's a huge caveat in the standard picture, and that is that we cannot predict ab initio what is the climate sensitivity of Earth, and therefore we cannot prove that this picture is correct. So what's the logic of the IPCC? What they do is they look at additional predictions that the model has, and in particular the two major predictions of these models are that the temperature increase should be unprecedented, because if it's mostly by humans, then it didn't happen in the past. And the other thing is that there is nothing else to explain the warming. If most of the energy budget change over the 20th century is anthropogenic, then it should be the dominant cause of the warming. But these arguments are, of course, wrong. Why are they wrong? Okay, so they basically reverse the logic. They say if the temperature increase is unprecedented, and if there's nothing else to explain the warming, then we can go backwards and then therefore claim that climate sensitivity is large, and with it predict large temperature increase over the 21st century. But these arguments don't hold water. The first one, the fact that it's unprecedented, was of course boosted with the hockey stick, which we know from the Climate Gate, which we now celebrate 10 years since it broke out. We know that it's not unprecedented. We also heard from Professor Scafetta that the Middle Ages, for example, were just as warm. This is another reconstruction based on boreholes actually measuring the temperature at different depth and solving backwards the diffusion equation. And you can see that past times, several thousand years ago, like in the Middle Holocene, it was even warmer than it is today. So obviously we know that the temperature increase is not necessarily unprecedented. The other argument, of course, is that there's nothing else to explain the warming. If you try to explain or run the models without taking the anthropogenic forcing into account, you cannot explain what has happened. This, of course, assumes that there is nothing else that we have been missing, but there is something, and that is the sun. Okay, so what I want to show you is that the real picture is different. We also have the sun taking place, and that would be the rest of the talk. But before that, let me address a few additional arguments that we often hear by people in the media or the IPCC. Of course, there are non-scientific arguments, like 97% of the scientists think whatever they think. It doesn't really matter because it's irrelevant. Whenever you have one scientific argument, it trumps any non-scientific arguments like this one. Of course, we see a lot of evidence for the warming. We see, I know, at glaciers receding, or I don't know what. We see polar bears stranded on floating on ice or doing whatever they're doing. So first of all, we heard from yesterday's talk that the fact that we see a polar bear stranded on an iceberg doesn't mean that there was even warming. But even if we see evidence for warming, because I know what glaciers in the Alps are receding, it doesn't tell you that it's because of humans. So this argument doesn't hold any water. Another argument that you sometimes hear is that, oh, we see CO2 signature in the stratospheric cooling, or more precise, the upper stratosphere cooling. And that's because if you have more CO2 in the upper stratosphere, you have more ways of radiating away the energy, and therefore it cools. So this is evidence of the radiative forcing effect that the CO2 has. It doesn't tell you anything about all the sensitivity and all the feedbacks that you have in the lower part of the atmosphere, and therefore this argument is not important. Another argument that we hear very often is that we see the heat in the oceans because we see the ocean, we can measure the heat in the oceans, and we can see that it has increased, and therefore it's evidence that it's anthropogenic warming. One of the things that they don't tell you is that if climate sensitivity is low, it means that the oceans can efficiently or more efficiently lose the heat, and therefore the amount of heat we should see in the oceans is actually lower. What that means is that in order to explain, if you have an additional source of heat, such as the sun, then you would see the combined effect of the sun and the anthropogenic greenhouse gases in the oceans, but a lot of it has already escaped. So just looking at the amount of heat that you have in the oceans also doesn't tell you anything about what the climate sensitivity, nor is it a signature, a particular signature that CO2 is the main source of this heat. Okay, so these arguments are just chaff which actually hide away the main caveat, which is we don't know what the climate sensitivity is from climate models. What we have to do, we have to look at a long, or say, empirical evidence, for example, long timescale variations in the CO2, and compare that to the temperature changes. Okay, so the picture I want to present to you is a little bit different. Solar activity increased as well over the 20th century. We can also measure and quantify the change in the energy budget associated with solar activity. And we'll see that it's about 1 to 1.5 watts per square meter between when the sun is less active and more active. So that's an additional contribution to the energy budget. So if you want now to explain what has happened in the 20th century, you need a climate sensitivity which is on the low side, roughly around 1 to 1.5 degree increase per CO2 doubling. And this is also consistent with empirical data that I will show you. Okay, so if the climate sensitivity is on the low side, it means that any future temperature increase will also be modest. Another thing which I personally don't understand, I'm not a nuclear physicist, but if I would have believed the story of the IPCC that we are at the brink of extinction, or what, all those doomsday children that we see running around nowadays, if I would have believed that, I would have said, just a second, there is a very clear solution to it, and that's nuclear power. We can immediately reduce most of our carbon emissions. So even if the IPCC story was correct, just the fact that we, even if the climate sensitivity is high, we don't need to ruin the economies and increase double or triple the cost of electricity just because there is a very clear solution. Okay, so that's my 2 cents on nuclear power. Okay, so let me start by, continue by showing you that there is empirical evidence that the climate sensitivity is low, and then I'll show you that we can actually quantify the effect that the sun has in order to complete this picture. So how do we know that climate sensitivity is low? We can look at different changes in the energy budget and see what is the ensuing changes in the temperature. One example, which was advocated, for example, by Professor Linzen from MIT, is the relatively small response that you find once you have large volcanic eruptions like Krakatau or Pinatubo or whatnot. If you look at what the climate models give you, they show you that once you have a large volcanic eruption and you put dust in the stratosphere, the temperature should decrease typically between 0.3 and 0.5 degrees, while if you look at the average temperature decrease following you can see that here at the bottom, following large volcanic eruptions. This is the average temperature, average in the several years before and after large volcanic eruptions. You see that the temperature decrease is about 0.1 degrees. So it shows you that the actual response of Earth's climate is much smaller than what the models predict. Another example is on completely different timescales. On geological timescales, there are large CO2 variations which have nothing to do with equilibrium with the oceans or things like that. It's CO2 variations because you have more volcanic activity on one hand or less volcanic activity, and then CO2 which turns into limestone and settles in the ocean and then recycled inside the Earth. So on large timescales, on long timescales, geological timescales, you see variations in the CO2 which are typically a factor of 10 or even more. This is the upper graph. Note that it's a logarithmic scale. So for example, 450 million years ago, we had more than 10 times the amount of CO2 in Earth's atmosphere on one hand, but then we can look at what the temperature was doing. And this is the lower graph. The lower graph is a reconstruction of the temperature using isotope ratios in fossils. And when you do that, when you reconstruct the temperature, you find that there were oscillations which actually have nothing to do with the changes of the CO2. So with this complete lack of correlation between CO2 and temperature reconstruction, you can actually place an upper limit of about 1.5 degree increase per CO2 doubling. Okay, it is much smaller than what the IPCC models give you. In fact, you can show that it's not really an upper limit, but it's a range, and that's because changes in the CO2 affect the acidity of the oceans, which affect the reconstruction of the temperature. So it's a delicate point, which basically tells you that a lack of correlation between CO2 and reconstructed temperature actually gives you a sensitivity range of 1 to 1.5 degree increase. Okay, so, but some of you might have seen Al Gore's movie, or science fiction movie, The Inconvenient Truth. And you see that in that movie, he showed us this graph where you have a reconstruction of the CO2 at the bottom and the temperature at the top based on ice cores. And you see this very nice correlation between CO2 and temperature. And it might fool you. It fooled Al Gore, but it might fool you to think that CO2 causes large changes in the temperature. But it's not the case, because nobody tells you that it's CO2 affecting the temperature and not vice versa. The real source of this correlation is the fact that there is an equilibrium between CO2 in the atmosphere and CO2 which is dissolved or in the form of carbonic acid in the oceans, and there's typically 50 times more CO2 in the oceans than there is in the atmosphere. And this equilibrium depends on the temperature, such that when you heat the temperature, you release CO2 and you change this equilibrium. So in fact, most of this graph is because CO2 is affected by the temperature, and you can see that when you have ice cores with a high enough resolution, you see that typically the CO2 lags behind the temperature changes. CO2 should have some effect on the temperature, but this graph doesn't tell you anything about it. Okay, so returning back, we have seen that there's also empirical evidence to suggest that the climate sensitivity is low. Now let's see what do we see is the effect that the sun has. Okay, so the sun is not a constant, it's an active star which changes its activity, and it's manifested through many things. For example, you change the number of sunspots, you change the irradiance by about 0.1%, you change the solar wind, you change the amount of X-rays, and various other things which are related to this non-thermal activity. So the sun changes, and we can see that changes in solar activity translate into changes in the climate. This is, we've seen this graph in the morning, but I think it's one of the most impressive graphs in paleoclimatology. You see solar activity reconstructed through carbon-14 in tree rings at the top, and this is a proxy of of solar activity, because carbon-14 is formed from cosmic rays coming from outside the solar system, but the flux of these cosmic rays is modulated by solar activity such that when the sun is more active and it has a stronger solar wind, less of these particles can hit the Earth, and we have less production of carbon-14. So this is basically a proxy of solar activity. The bottom graph is a proxy, or it's the ratio of oxygen 18 to oxygen 16, which is a proxy of temperature, because water with oxygen 18 is heavier than water with oxygen 16. So the evaporation rates from the oceans are different for the two water molecules, but it's temperature dependent. So in this case, it's a proxy of the temperature in the Indian Ocean, because this is reconstructed from oxygen 18 in stalagmites in caves in Oman, which is in the southern Arabian Peninsula. So you see a very nice correlation, and it tells you that either the sun is affecting the climate, or maybe the climate on Earth is affecting the sun. It was a joke. Okay, this is another example. In this case, it's a reconstruction of the temperature in the northern Atlantic. What you have here is it's called ice-rafted debris. When it's colder, you have icebergs floating further south, and when they melt, they leave their ice-rafted debris, the dust, at further southerly latitude. So if you take cores from the sea floor, you can actually see whether it was colder or warmer. And again, you can compare that to carbon-14 from tree rings and see an extremely nice correlation showing that the sun affects the climate in the northern Atlantic. So it affects the climate in the northern Atlantic, it affects the climate in the Indian Ocean, and it affects the climate actually globally. Okay, this is another example on a little bit shorter timescales. You can look at the rate of change of the sea level using tide gauges. This is in the blue line with the arrows in the gray area. And in red, you see the activity of the sun. So I think it's quite clear that when the sun is more active, the oceans are rising, whereas when the sun is less active, the oceans are falling. Okay, so we see that the sun has a large effect on the oceans, or vice versa. And just kidding, the oceans don't affect the sun. But the nice thing is that on short timescales, most of the change in the sea level is because of heat going into the oceans and thermally expanding the oceans. So basically, we can use the oceans now as a huge calorimeter to quantify the effect that the sun has and see that it's very large. If you don't believe this graph, you can look at other data sets. Since that work was published, we now have very nice satellite data, satellite altimetry telling you what the ocean, sea level is, and you can compare that. This is the ocean sea level without the linear increase. You can see that without the linear increase, almost all the sea level change is because of the sun and El Nino. You can also do something else. You can take the ocean a heat content with buoys that measured the ocean, the temperature at different depths from the 1950s. And you can correct that for changes in the you can differentiate it to get the amount of heat that went into the oceans every year, and you can correct that for the amount of heat because of volcanic forcing. And this is the graph you see at the top. And at the bottom, you see solar activity. It's one parameter which describes, in this case, it's called the solar modulation parameter, which is how much is the solar wind affecting the cosmic rays. But again, you see that with the 11-year solar cycle of the sun, every time the sun is more active, more heat goes into the oceans, and vice versa. Okay, so we know for sure, how sure I would bet my house on it, that the sun has a large effect on climate. I'm joking, my wife wouldn't let me, but my half I could, yes. Anyway, so you can look at the amount of heat that goes into the oceans with different data sets, where it can be satellite altimetry, tide gauges, ocean surface temperature, the heat content I showed you. You can also look at how much the clouds are changing and calculate the amount of heat that goes into the Earth system because of that. And you find that between solar minimum and solar maximum, the change in the energy budget is around 1 to 1.5 watts per square meter. How does that compare to the total solar irradiance? The total solar irradiance is an order of magnitude smaller. What that tells you is that it cannot be changes in the total solar irradiance. It has to be another mechanism which links between solar activity and climate. Okay, so even though the IPCC is artificially trying to minimize the effect of the total solar irradiance by removing the effects of, say, the Maunder minimum and things like that from the total solar irradiance, it's not really important because we know the effect is not from the total solar irradiance. Now, over the 20th century, solar activity increased. Here we see, again, the solar modulation parameter, which tells you how much is the solar wind affecting the cosmic rays. And you can see the 11-year solar cycle, but the 11-year solar cycle is sitting on secular changes in solar activity. In particular, over the 20th century, solar activity increased. Now, if you have changes of about 1 watt per square meter because of changes in solar activity from, say, solar minimum to solar maximum, also this secular increase in solar activity over the 20th century should translate into changes in the energy budget, which the IPCC is doing its best to ignore. Now, this is the changes in the radiative forcings that we see in the IPCC report, the last one, the fifth assessment report. This is the changes in the energy budget associated with different components. Again, at the bottom, we see what the IPCC is saying the sun has contributed, but we know for certain, by having measured the amount of heat going into the oceans, that it should be somewhere here. Okay, so this is the big elephant that the IPCC is ignoring. Now, what is this mechanism? We're going to hear more about it from Henrik. The mechanism is as follows. It turns out that the solar wind and modulating the cosmic rays is not only the proxy for solar activity, it is also the actual linking between solar activity and climate. When the sun is more active, it has a stronger solar wind. And as a consequence, we get less of these high energy particles which originate from supernovae, from our galactic vicinity, such that a stronger solar wind will give us less cosmic rays. Less cosmic rays produce less ions in the atmosphere. They are the dominant source of ions in the atmosphere. Well, here in this room, it might be a radon emanating from the concrete, but outside the planetary boundary layer, it's all cosmic rays. And now we know that these ions play a role in the nucleation and then the growth of the cloud condensation nuclei, such that when the sun is more active, we have a stronger solar wind, we have less cosmic rays, less ionization, less cloud condensation nuclei, and therefore clouds with fewer droplets. These clouds with fewer droplets have a smaller total surface area, so they reflect less of the sunlight, such that more of the energy can penetrate the climate system and it's warmer on Earth. So a more active sun gives you a warmer Earth. Now, do we see that? Again, we're going to see evidence in the next talk. We can have, for example, gusts in the solar winds, which give you reductions in the cosmic rays, which translate into changes in the cloud parameters. I'm not going to elaborate because Henrik is going to do that after me. However, we also have evidence on long timescales. We can look at changes in the cosmic ray flux which have nothing to do with solar activity. Just because as the Earth is orbiting the galaxy, the environment around us changes, and sometimes we have more supernovae and more cosmic rays around us, and sometimes we have less. And over the past billion years, we can reconstruct the flux of cosmic rays reaching us using meteorites, using iron meteorites. And when you do that, you find a very clear periodicity of around 145 million years. Basically, what happens is that every so often, we pass through spiral arms of the Milky Way. And when we pass through a spiral arm of the Milky Way, there are more supernovae, more cosmic rays, more clouds, or clouds which are whiter, and therefore it's colder on Earth. And in fact, over the past billion years, every about 150 million years, in sync with the passage of the spiral arms, we see that it's colder on Earth. So here at the bottom, you see a reconstruction of the cosmic ray flux, and here you see a reconstruction of the temperature, and the cosmic ray flux explains the temperature variations. On a little bit shorter timescales, we are also moving up and down the galactic plane. We can reconstruct the temperature. You can see that here. These are the 150 million year oscillations, but overlaid on that, you see faster oscillations of 32 million years, and that corresponds very nicely to the fact that we are oscillating up and down the galactic plane. The phases agree. There's also a secondary modulation because the distance from the galactic center changes, and we all see that in the data. So what does it imply to the understanding of 20th century climate change? When the sun, the standard picture is such that most of the radiative forcing is anthropogenic, the climate sensitivity is relatively high, and therefore it explains the temperature increase that we have seen. But if the climate sensitivity is high, it would tell you that the 21st century temperature increase should be high as well. However, we have seen that there's another large contributor of changes in the energy budget, and that's solar activity. So the net change in the energy budget is much larger, and therefore, in order to explain the same temperature increases over the 20th century, you need a climate sensitivity which is low. And if the climate sensitivity is low, and again, which is consistent with empirical data, then the temperature increase over the 21st century should be low as well. How am I doing with time? I should stop. Okay, so I won't tell you what will happen in the future. I can tell you that you can fit the 20th century very nicely with a climate sensitivity which is very low. You can integrate forward in time and see that the temperature increase is going to be relatively modest. Okay, so let me end with the summary slide. The main arguments that the main arguments that we have seen in the standard picture are wrong. They don't support this picture, and there's a very big caveat. This big caveat is that if there is another climate driver, then in order to explain what has been going on, you need a low climate sensitivity. And I showed you the evidence that the sun is this additional climate driver, and therefore future climate warming is going to be modest. And now I'll give the stage to Henrik, and I think the Q&A is going to be afterwards, right? Okay.
Your computer.
Vielen Dank, Nir. Als nächstes kommt Professor Dr. Henrik Svensmark. Professor Svensmark ist Direktor des Center for Sun Research des Danish National Space Center. Er war von 1988 bis 1993 an der University of Berkeley, California, am Nordic Institute of Theoretical Physics und am Niels Bohr Institut tätig. Anschließend arbeitete er am dänischen Meteorologischen Institut. Svensmark wurde zusammen mit Eigil Friis Christiansen 1997 durch Arbeiten zu einem Zusammenhang zwischen kosmischer Strahlung und dem Klimawandel bekannt. Sie stellten dies als Kosmoklimatologie vor. Svensmark untersuchte den Zusammenhang zwischen kosmischer Strahlung und der Wolkenbildung in der unteren Atmosphäre. Und in beiden Fällen stellte er teilweise überlappende Zusammenhänge fest. Im Falle von Sonnenflecken war dies bereits früher vermutet worden, so bereits von Wilhelm Herschel, anhand des Mäander-Minimums, deren Parallelität zur kleinen Eiszeit im 17. Jahrhundert lag. Das zur Überprüfung von Svensmarks Theorie durchgeführte Projekt SKY legte die Grundlage für das erst 2014 am CERN abgeschlossene Forschungsprojekt Cloud. Und das zum Thema Forschung, was ich anfangs kurz angeschnitten hatte, als ich Henrik Svensmark anfragte für die Konferenz, meinte er, ja, ich habe bis jetzt noch keine neuen Veröffentlichungen gemacht, was ja voraussetzt, dass die neue Forschung abgeschlossen ist. Und da ist das, was man, das muss man betonen, das hatte ich das letzte Mal auch schon mal erwähnt, dass praktisch die Forschung, die nicht in den Mainstream passt, die Forschungsergebnisse, die nicht die übliche These des ausschließlich menschengetriebenen Klimawandels unterstützt, ebenso gut wie keine Forschungsgelder mehr bekommt. Und wir hatten das schon das letzte Mal erwähnt, dass einer der Teilnehmer unserer früheren Konferenzen das mitbekommen hat und es ermöglicht hat, dass hier Forschung dann privat weitergeführt werden konnte. Also für diejenigen, die hier dabei sind oder das auf YouTube sehen oder im Livestream, vielleicht fragen Sie Ihrem Bekanntenkreis nach, ernst gemeinter Vorschlag, und bitte auch, ob hier nicht mal weiter die Forschung unterstützt werden kann. So, without much further ado, Henrik, it's your turn.
Thank you very much. Can you hear me? I'm going through. Good. So I'm going to continue more or less where Nir stopped, or at least put some physics into, the mechanism that we have been investigating for a number of years. I should say that we are a small group that have been working on this. Nir is part of it, then my colleague Martin Enghoff, and actually my son Jakob has also been part of this. Nir and I, we at some point a number of years back, we decided to collaborate because we had been chasing each other's tails for quite a while. And it was annoying that Nir, he published things that I was working on before I got to publish things. So that's why we... Is that a problem? So I'm being fixed. Can you hear me now? Okay. So now I can hear myself. I'm going to talk about this link that we have been working on for quite a while, the empirical evidence for a link we have heard a lot about today already. But we have to understand the microphysical link, why there should be such a link between cosmic rays, cloud, and climate. And finally, I will also say something about the implications on the long time scales, just as Nir did, because I think it's really an interesting possibility that we are exploring. So the main character in all I'm going to talk about today, it is actually cosmic rays. And what are cosmic rays? Well, they are what we call a non-terminal population of relativistic particles, which means that they are moving at the speed of light, more or less. But they are actually quite important in the Milky Way. They are important for the stability of the interstellar media. So it has a pressure which is more or less the same as the pressure from gases. And they are everywhere. They are in the Milky Way, they are in all galaxies, they are in intergalactic space. So why should we care about these cosmic rays? Well, they are important, but the most interesting thing is that they seem to be important for climate. And what I will show you, they might even have some impact on the conditions for life here on Earth. And of course, there's a lot of interesting physics, but a little bit of the history. Already Coulomb in 1785, he found out when he charged one of these gold leaves here, when it became charged, he discovered that the system was discharging much faster than you would expect from just a leak current. So something was in the air that made this instrument, which is called electroscope, to discharge. And of course, in 1896, Becquerel, he discovered spontaneous radioactivity, and later Marie Curie and Pierre Curie, they discovered polonium and so on, radioactive elements. So quite early, we knew that there was something that, some kind of a dark current in the absence of any sources, and Rutherford suggested that most of this dark current was actually from radioactivity. Then there were some ideas. They didn't know whether it was coming from the Earth, from radioactive elements, or it came from the atmosphere. And there was a test in the Eiffel Tower where they actually saw, or he saw that the amount of this dark current, it was going down by a factor of 2. So he suggested that it came from the Earth. The things were not really clarified before Victor Hess in 1912. He made a number of balloons where he took an instrument up to about 5 kilometers or something like that, and he saw that it increases as you go higher up. So he made the observation that this is most likely to be explained by the assumption that the radiation, it comes from above our atmosphere. And that was sort of the start of cosmic rays. Here you see a spectrum of cosmic rays, and that's one of the reasons there's some really interesting physics behind this. Here you have the intensity of that is the flux of cosmic rays. It's more than 30 orders of magnitude. And then you have the energy, and up here you have 10 to the 20th electron volts. These are macroscopical energies. It's really high energies. But you see that these particles are of the very high energy are only happening, once per square kilometer per year. So these are very rare. As we go higher or lower into the energy, we have 1 particle per square meter per year. So they are also very rare. So we have to go up to this low part before we get particles that are relatively frequent. And these are the ones that enters into the atmosphere and do most of the things that we are interested in with respect to climate. So one of the big problems has been what is accelerating these particles? How do you get these high energies? And the idea is it has to do with supernovas. So when you have a supernova, you get this shock front here, and the particles, they diffuse, and each time they pass this region here, they add a little energy, and that is what we could call a galactic accelerator of these particles. So this is the origin of all the lower energies that we are interested in. They come from supernovas. So when we have a particle that goes into the atmosphere, it creates a shower structure where you produce a lot of the different types of particles, and this in itself is very interesting. What is interesting in this context is that we produce ions in the atmosphere. The ions are important when we talk about clouds, as I will do in just in a minute. But you also produce new isotopes, and you've already seen that, we can use these isotopes to say something about how the sun has changed in time. If we go back, because some of the carbon-14, for instance, goes into a tree, and you can then look at a certain tree ring and see how much carbon-14 there is compared to carbon-12, and that says something about the solar activity back in time. And the reason is, if we look at the solar system, where we have the sun in the middle and we have the planets, we have the sun's magnetic field, and that works as a shield against cosmic rays that tries to enter into the solar system. If the sun is very active, fewer cosmic rays can enter into the solar system. So the sun can actually modulate how many cosmic rays are entering or arrives in the top of the atmosphere. Now, the thing is that each time you have a change in the intensity of cosmic rays, then there is a change in climate. And there's so much empirical evidence. This figure you actually have seen already a few times, but it's over the Holocene period, that is the last 10,000 years. And you can see where you have the drift ice, that is over the North Atlantic, and you have the carbon-14, and you have this beautiful correlation. So this is just one example. The other example I'm showing here is the last 1,000 years, where you see here the medieval warm period, the little ice age, and then the modern period. And if you compare this with solar activity, which is actually carbon-14 and beryllium-10, another cosmogenic isotope, you actually see a very nice correlation between the two curves. And it all suggests that, this is part of this empirical evidence that says that if you have a change in solar activity and you change the cosmic rays, it looks as if climate is changing at the same time. So, more historically, but also what is going on presently, is that one idea is that, of course, it's solar irradiance that is influencing climate. However, the change in solar irradiance, at least from the IPCC, is so small that it will not really have any effect. You can see here that from 1880 to present, they say that this is the size of the effect of the sun. And if this is the only way that the sun could influence climate, it would be so small that the effect of the sun would be something that you could just ignore. There are, of course, ideas where you talk about having even larger changes in solar irradiance. For instance, on the order of 0.4%, which means that you would have about on the order of 6 watts per square meter. This is, of course, large. But in order to have such a large change in the solar irradiance, you have to have changes in what we call the quiet sun's irradiance. And it turns out that when you look, for instance, at these, we call them spectrohalograms of the solar disk, and you look at the quiet part of the sun, then over the last 100 years, where you have these nice photographs, it does not look as if the quiet irradiance is changing. So it seems to be inconsistent that you could have such large variations in the solar irradiance, and that's at least how I see it. Now, recently, when we talk about solar activity, we have had the observations of sunspots going back 400 years of that order. But and then over the last 400 years, in all the reconstructions, you had sort of an increase in the solar activity measured by sunspots. But there have been some reconstructions. One is here by Svalgaard and Schatten, where they sort of made a recalibration of these sunspot numbers because there's been different observers, and they got that the solar activity is more or less the same when you go back to the 17th century. So and that was claimed as if the sun cannot have had any influence on climate change. But if we look at the cosmic ray flux, and this is beryllium 10 that you have up here, we actually see that there has been a decline over the last 400 years, or this is 600 years. And this decline, this corresponds that you have a more active sun, so it screens better against cosmic rays. So solar activity has increased over this period of time. So the cosmic rays, which are measured here, seems to indicate that there has been an increase in solar activity over this period. So what Nir showed was that we had these, we could see how much energy, we could quantify how much energy goes into the oceans, and that we need some kind of a amplification mechanism in order to explain what's going on. And one of the big or the important candidates for this is actually changes in clouds, because the changes that we see are of the right order. Solar irradiance, on the other hand, seems to be too small. So, and here we have satellite observations of the solar irradiance here. So we know that this cannot explain what we are seeing here. So we have to have an amplification mechanism. And the obvious thing that we have been talking about in this beautiful picture here, this is more or less this month. You see what, if you look at Earth from space, you see clouds. They are everywhere, they're very dynamic. So they are probably very, very important for the radiative budget. The net effect of clouds is to, what's that? The net effect is to cool square meter. What is going on here?
Take this one.
So, yeah. So the net effect is to cool the Earth with about 30 watts per square meter. So if you have a systematic change in the cloud cover, it will be a very effective way of changing the Earth's energy budget. And I mean, many things seem to indicate that's going on. Here you see what actually started much of this work, which is a correlation between cosmic rays and satellite observations of clouds. So this is from 83 until present, and the red curve here is the change in cosmic rays as measured by neutron monitors. The change that you see here is as because of the solar activity. So this is the 11-year solar cycle you see. So when you have a small amount of cosmic rays or fewer cosmic rays, it's because the sun is very active. Whereas here you have a solar minimum and you have much more cosmic rays coming in. The blue curve is changes in low clouds over this period. And, I always say that maintaining this type of, satellites over such a long period is very difficult. So there are some calibration problems, and that's why it ends at 2006. So if there is a link between cosmic rays and cloud, what is the link? Well, the idea is that we have cosmic rays entering into the atmosphere. It makes charges, so it makes ions, and the ions, they sit on gases, and the gases start to clump together, so you get these clusters. And the clusters are then more stable because you have these ions in the clusters. And then subsequently, these are only about 3 nanometer. They have to grow up until about 50 nanometer. And then they can work or act as a cloud condensation nuclei. So if you have these cloud condensation nuclei, then water vapor can condense. And in order to form a cloud droplet, you have to have these cloud condensation nuclei. And if you change the number of cloud condensation nuclei, you change the properties of clouds. And you can see that very beautifully in the next picture. What you see is the satellite observations, and you see this is a region over the oceans where you have low clouds, and all these stripes is ships sailing along, and they are pumping out, from the dirty fuel, aerosols, which are large enough to become cloud condensation nuclei, and so they are changing the cloud properties in these areas. And this is quite dramatic here, but smaller things can also do it. So we had this theory, and we could now test it in the laboratory, and this is something we've been doing over the last 15 years, more or so. What you see here is one of the first results that we got. So what you have here is the ionization. So this corresponds to the cosmic rays. So we can increase the ionization in our chamber, and then we can measure how many small particles that we are producing when we increase the ionization. And you see that there is some linear correspondence. So you increase the ionization, you produce more of these small aerosols. And at first we thought that maybe we are at home now, because now we have a mechanism. We just produce more small aerosols, and then the aerosols grow to cloud condensation nuclei, and that would change the properties of clouds. But it turns out that these very small aerosols has to grow to almost 50 nanometer. And if you produce more of these small aerosols, there's a big chance that some of them will get lost to the larger ones. And if you had all these climate models that tried to investigate this effect, and they actually saw these small aerosols did not survive to cloud condensation nuclei. So that was a very negative result. So what we did was try to see if we could mimic these conditions in an experiment. So first we had our experimental setup. We put in some small aerosols, and then we put in some extra aerosols, and then we see what is the fate of these small aerosols as they grow. And it turns out that as they grow, they get lost to the other aerosols and to the walls. And when they are about the size of cloud condensation nuclei, the relative change of the number of aerosols is more or less the same as when we started. And this is in complete agreement with the computer modeling. So, where is that? Oh, I should show you this one. So when we did the same experiment, but with ionization in the chamber, then we actually saw that all the particles, they grow to cloud condensation nuclei. So there is a mechanism, or at that time we realized there had to be some kind of a mechanism that could explain this. If we look at the climate models here, these are, here you have the diameter of the particles. So here you have the very small particles, and here you have the cloud condensation nuclei. And you would expect that if you add, about 5% more small particles, in order to get what we expect from observations, then the models should show that the number of particles would end up there. But what you see is that this is what we would expect, and this is what the models are showing. So that would mean that it's completely negligible. So we spent actually a number of years trying to figure out what was going on. And I'm not going to go through it in any details here, but the result is that ions are also helping the growth of cloud condensation, the growth of aerosols into cloud condensation nuclei. So there is a process where we both produce new aerosols, and the ions are helping the formation of cloud condensation nuclei, and we believe that might be the case. So the obvious question is, I mean, people were saying, okay, this is your experiment, but it probably doesn't work in the real atmosphere because there are so many aerosols and there are so many processes in the real system. But it turns out that you can actually observe the whole chain in the atmosphere, because sometimes you have these coronal mass ejections that you see here. This is the sun. You cannot see the direct light, but you can see the atmosphere. And you have some plasma that is thrown out, and then the cosmic rays all of a sudden makes a drop, and it could be on the order of 30%. Here is another nice picture of some of these disturbances that you see from the sun, how they are moving out into the interplanetary space, and they are affecting the cosmic rays. And this is the figure that also Nir was showing. But the interesting thing is that the red curve is the drop in cosmic rays, and this curve here is the change in aerosols. So all of a sudden we have fewer aerosols going into the atmosphere when we have a drop in the cosmic rays, and we also see the change in liquid water. This is liquid water in the clouds over the oceans. We see it in a different satellite set. This is the MODIS data set, and this is the ESCIP data set. So we see this effect everywhere. So we can say that we see the whole chain from cosmic rays to aerosols to clouds. And the changes that we have are sufficient to explain, I mean, they are in the right order of what we would expect. So let me summarize the mechanism. The idea is that we have the galaxy that produces cosmic rays. It produces ions. Then we have the sun. It helps the formation of sulfuric acid. But because of these ions that we have, it helps the stabilization of small clusters, which then subsequently grow, also because of the ions, into cloud condensation nuclei. And when we have the cloud condensation nuclei, we change the cloud cover, and by changing the cloud cover, we can change the, how much energy goes into the Earth's system. So that is more or less the mechanism that I've been talking about. And now the last few things, which is on a completely different time scale, but I think it's also very interesting. So cosmic rays, we're talking about modulation by the sun, but now we're talking about star formation and the number of supernovas that are around the solar system. So I did some work where I looked at, tried to reconstruct cosmic rays over the last 500 million years. You can see these waves that you have here going up and down. And the thing is, Nir showed that it had a big influence on climate. What I'm going to show to you is that it seems as if it also has a big influence on the conditions for life here on Earth. And in 2008, there was a very large study where they looked at the marine invertebrate and looked at the changes in diversity over the last about 500 million years. And the results look something like this. You see, this is more or less present, and this is 500 million years back in time. And you see the changes in the number of genera. They're going up and down. And a big question has been, what is the cause of such changes? And there's been many ideas, from sea level to, of course, volcanic eruptions, plate tectonics, and so on. But it turns out, if I take just two things, which is the sea level and changes in climate, I can actually explain things. I get a remarkable result. Let me show you what I mean by that. So here you see the sea level change over the last 500 million years. If you notice here the axis, this is a real sea level change. This is hundreds of meters going up and down. So this is, you see that if we go back, about 70 million years, the sea level was much higher several hundred meters than it is present. And why is that important for the number of genera? Well, when you have a higher sea level, you have the continent, they are flooded. And that means that you can have species inside here, and they are sort of isolated from each other. And you have more regions where you can have different species. That means that if the sea level goes up, you can have more species. So that is the idea why the sea level enters into it. The other thing that enters was climate. And if we assume that climate is related to this change in cosmic rays that you see here, then when I normalize the number of genera with the sea level and then plot it. So this is this curve here is only astrophysics, and I then show you a curve which is only related to the Earth and the genera and sea level. You see that there's a beautiful correlation. So it indicates at least that this mechanism that we are talking about might be extremely important, and I think therefore it is necessary to understand these things in a much better way. So this is the last thing I had to say. So variations, each time you have a variation in cosmic rays, suddenly you have a change in Earth's climate. And I mean, everything suggests that clouds are the real player in this. And clouds are, of course, the least understood part of the climate system. We believe that we understand this mechanism to a much larger degree than when we started. Involves ions and aerosol formation. And by having the aerosols, we are linking to clouds, and therefore, of course, the energy budget of the Earth. And the final thing is that if you understand this link, it seems to have implications for our understanding of the changing conditions that we have had for life here on Earth, not just climate. Thank you.
Okay. You just go on stage? Yes. Okay. You have a headset here for your ex. Gut. Erschöpfend, alles beantwortet. Die Fragen, okay, nochmal. Sie stellen auf Deutsch Ihre Frage. Wer unbedingt auf Englisch sprechen will, bitte, aber wir haben 3 professionelle Damen, die ich immer noch nicht richtig mit Namen vorgestellt habe. Weiß gar nicht, ob ich das soll. Und bitte, Ihre Fragen, da sind welche. Okay.
Konrad Rotscher, Austria. I want to know why you did not point out to the changes of the magnetic field and the possible impact of solar winds on this magnetic field of the Earth.
Yeah, so I didn't talk about the Earth's magnetic field. I guess that's what the question. So the Earth's magnetic field is, of course, also important because it regulates how many particles that enters into the atmosphere. In the polar regions, it's very easy for particles to go into the atmosphere, whereas the Earth's magnetic field is also having an effect. It's not something that we have done a lot of work on, but we know that it changes.
The thing is that on the timescales because the magnetic field of the Earth stops particles which are typically at energies below which you need in order to penetrate the whole atmosphere, switching off Earth's magnetic field altogether doesn't change the atmospheric ionization by that much. It is comparable to what you get between when the sun is not active and when it's active. However, on the long timescales that the magnetic field of Earth changes, you have other things, such as the Milankovitch cycles, which affect as well, and therefore the signal that you get from changes in the Earth's magnetic field are not dominant on any timescale. So you have to be more careful when you're looking for them. But yeah, you should see some effect, and there are claims that you see effects because of changes in Earth's magnetic field.
Okay, Müller-Plath from Berlin. Thank you for your very interesting talk with convincing us of a very good alternative hypothesis. I have a question to Professor Svensmark concerning statistics. You showed us a slide with a strong correlation between cloud cover and galactic cosmic rays. I think you remember that slide. Would you mind to put that on again?
Sure.
Or if it takes too long, I can.
It come up.
Yep. Yeah,
one?
that. The range of cloud cover is only between 27 and 30%, and I think that's a quite small range. And my question is, how is it measured, cloud cover percentage, and could you comment on the accuracy of that measurement?
Yeah, this is a particular data set which is called the ISCIP data set, the International Satellite Climate Project. So this is measured using all the geostationary satellites and at least 2 polar orbiting satellites from NASA. And the problem is that this is a very long time period. So the satellite, they fail at different times. So you have new generations of satellites coming up. So it's very difficult to maintain a calibration over this long period. And the calibration has been, we tried to correct this data set with the calibration. So the reason I'm showing you this is simply because it was sort of the initial start of the whole idea. And I think that the first part of this figure is okay, but now we know that the calibration is gone in this data set. The change, which is on the order of these 2%, is really what you need. I mean, you have to have this accuracy in order to see what we are talking about. So it has to be in this order. And it is on the limit of what you can do with satellites. So if you have a single satellite and only measuring with one satellite, it actually only comes back to the same point every 12 hours, so that you don't know what's going on for at least 12 hours. So you have to have many satellites, and it's really difficult to calibrate this whole system. So at the moment, we don't have any satellite systems that can actually measure these things with the needed accuracy. So that's a real problem. And that's why we went over to look at these short time changes over 20 or 30 days, because here we don't have these calibration problems. Okay. Ja, dann.
Könnten Sie uns vielleicht noch etwas Näheres darüber mitteilen, wie die kleinsten Aerosole von 3 Nanometer aufwärts sich zusammenraufen, um nachher ein Cluster von 50 und höher zu bilden?
Well, one of the most important molecules for this clustering is actually sulfuric acid. And sulfuric acid is sort of, it's produced completely naturally in the atmosphere. It's mainly from algae over the oceans that when they die, they send out what's it called, DMS. And that is then transferred into SO2, sulfur dioxide, and then it reacts with ozone and water and becomes sulfuric acid. It's a completely natural mechanism. But the sulfuric acid, it's like the super glue of the atmosphere. It really likes to stick together. And if you have an ion on it, because it's a polar molecule, it makes the stability much stronger. So when you have few or less sulfuric acid, then by having the ions, they actually stabilize these small clusters. As soon as they are stable, then they can start to take up all kinds of things, and water and more sulfuric acid molecules, other organic molecules, and so on, and then they slowly grow. But when they are small, it is a dangerous life for the small aerosols because they get eaten by larger aerosols. So that's the fate of many of them. So it's not all of them that becomes cloud condensation nuclei. You have any comment? Okay, I get tired in my arm. Yeah.
I have a small question about the clouds and their regarding their role on or their impact on the climate or temperature. Especially, could you tell me or could you talk about the reflection of heat rays coming from the Earth compared to the reflection of heat rays directly coming from the sun?
Sure. Clouds has two effects. They both heat and they cool the surface. So the short wave is that they reflect the short wave, the sunlight, out to space again. But we all know that when there is a cloudy evening, it's always warmer, and that's you have a strong greenhouse effect from clouds. So you have two large effects. One is the solar effect, where you have the radiation going out, and then you have the greenhouse effect of clouds. So you have two large, one is warming and one is cooling. So you have to subtract these two from each other, and then you get about, for low clouds on the order of 15 watts per square meter cooling. So the cooling is what wins in the end. Oh yes, it changes with the height of the clouds, because if you have high, thin clouds, then because they are thin, solar radiation goes through, so their net effect is actually a heating of the Earth, which is not a very large effect. So the dominating effect of clouds is actually from, the low clouds over the ocean, marine stratus clouds, which are everywhere. They are the ones that are cooling the planet.
Assuming that the Arctic region is warming up, and if we know that the solar wind follows the magnetic field lines, do you see a correlation between your theory and the Arctic warming?
You shouldn't, the fact that the magnetic field lines funnel the solar wind to the poles, which is why you see the aurorae at polar regions, has nothing to do with this mechanism, because most of the ions in the atmosphere are formed from high energy particles with an energy of typically 10 or 15 GeV or more, which are the energies of which the secondaries can penetrate the atmosphere. So the solar wind doesn't have any direct effect on the climate. It's all stopped in the top tens of kilometers in the atmosphere. It is true that it stopped mostly in higher latitudes, but it doesn't have any effect on lower altitudes. Now, the reasons that in any climate model or any mechanism, most of the warming of the polar regions is anyway not by direct heating from the sun at these latitudes, but how effective can you advect energies from tropical regions to high latitude regions. And this basically depends on the amount of water vapor you have, because most of this energy transport is through a latent heat of water vapor. You evaporate water in tropical regions. You evaporate the tropical regions, it takes energy, and then when you condense the water vapor, you release this energy. So any mechanism that heats the Earth will tend to heat the polar regions more, and so this is not a signature for any particular mechanism.
Okay, thanks for great presentations, Nir and Henrik. I have a question on sunshine hours. We heard how complicated it is to measure the clouds by satellite, and there's the low clouds, the high clouds, and so forth. can you do anything with the sunshine hours as measured in the weather stations? And have you done any regional differentiation that there may be trends that are different in different regions?
No, the short answer is no. The thing is that we were really interested, I mean, after we found large-scale variations, which, I mean, we're not interested in local variations. As interesting as it may be, we're interested in the global effects and in evidence for the particular mechanism, the fact that it's through cloud cover and cosmic rays. So it could be that, you know, there are some effects in, you know, in the UK or in Germany or in, you know, Patagonia. But it's not something that really interests us directly. We want to see the global effects. So it could be that you can use sunshine hours to get some handle, but because we expect the effect to be larger over oceans, that data set would probably be somewhat incomplete for us and therefore not necessarily relevant.
Thanks.
So my question aims towards Professor Svensmark. You just mentioned that the net effect of cloud building is a cooling one. So if I'm following rightly your assumptions, then actually the Earth has on long term a self-regulatory effect. That means like the more solar activities, the more clouds, and then it cools again. So on long term, we should actually cool if the activity grows, or how can I interpret it?
Well, I mean, there are of course some feedback mechanisms, no doubt, which is something that we don't know. I'm not sure that there's a self-regulating mechanism. I don't know what you're saying here.
There are feedbacks in the climate system, but I think the fact that climate sensitivity is relatively on the low side just tells you that they are not as large, they're much smaller than what the IPCC is advocating. And basically what it means is that there are no large net feedbacks. There are feedbacks to the clouds, which have to maybe cancel out other feedbacks, like that of water vapor. So it's a kind of a cloud feedback that stabilizes the system. The cosmic rays are then an offset knob that offsets whether you're going to have more clouds or less clouds. With regards to the first part of your question, I think in the future, it is true that if you have, now that the sun is becoming less active, we should expect a negative change in the energy budget, which would drive towards cooling. But again, there is also the effect of CO2, even though it's much smaller than what the IPCC is telling us, it is still there. So I won't necessarily expect the temperature to now decrease by, say, 1 degree or anything like that in the near future.
Mein Name ist Dietrich Bittel von Eickel. Ein besonders wichtiger Punkt wäre, meine ich, hier die Frage, wie hoch ist der Effekt der kosmischen Strahlung auf den Anstieg der Globaltemperatur seit der kleinen Eiszeit? Das ist ja die wesentliche Frage. Ich habe den Effekt der CO2-Emissionen seit dieser Zeit auf 0,2 Grad berechnet. Der Rest, egal wo dann, wie hoch der Anstieg nun gewesen sein mag, kann dann nur von der Sonne kommen. Aber lässt sich der einigermaßen quantifizieren?
You're quantified it.
If you try to simulate the 20th century by leaving things like the climate sensitivity as a free parameter, and the effect that the sun has as a free parameter through cosmic rays or through whatever, you can try to get or ask the question, what are the values of those different parameters that best fits the 20th century? And when you do that, you realize that you need a climate sensitivity, which is, this is something I just briefly flashed over, of 0.9 plus or minus 0.3 degrees, which is consistent with the other empirical data I showed you that gives you around 1 to 1.5 degree increase. So when you try to when you take this result, when you best fit what happened to the 20th century, and you leave the climate sensitivity as a free parameter, you find that about half or 2/3 of the warming is natural because of the increase of the sun, and only and the rest, which is 1/3 to 1/2 because of humans.
Mr. Svensmark, have your findings been discussed or even refuted by scientists who work for the IPCC? Have they been discussed publicly or even refuted? Have you heard any arguments where they think you are wrong or you went into the wrong direction? Or has it been ignored?
Yeah, I mean, this mechanism is discussed in the last IPCC report, and they used a author which is spent more or less his whole scientific career in criticizing what we are doing. So yes, it has been discussed, and it has been said that you know, it's crazy and we can't ignore it. I mean, basically the conclusion is that it's something that should be ignored, but it is discussed.
The thing is that even though we have very good evidence to quantify the effect that the sun has, and I think we first done it around 2008, it was totally ignored by the IPCC. So instead of admitting, okay, maybe there is a mechanism we don't understand, but we see that the sun has a large effect, what they say is that we don't understand the mechanism, even though we now think we almost have a complete picture. They say we don't understand it, and if you don't understand it, it must be wrong, and therefore we ignore the rest of the data that shows you that the sun has a large effect. So this is basically the state, but maybe I'll quote Al Gore in his movie. He quoted an economist called Upton Sinclair, who said, you cannot convince people in something when their job depends on them not understanding it. So I think this basically summarizes why the IPCC is ignoring the fact that the sun has a large effect, because it completely invalidates the main arguments.
Ja, hallo. Ich mache auf Deutsch. Wir haben gestern gehört, dass Susan Crockford aus Kanada, die Eisbärforscherin, wegen ihrer Forschungsarbeit und der darin enthaltenen falschen Ansichten gegangen wurde. Wir haben eben von Ihnen gehört oder in der Vorrede gehört, dass Sie weniger Forschungsmittel bekommen oder fast keine Forschungsmittel bekommen. Aber Sie sind immerhin noch an der Universität. Wie ist die Situation in Dänemark und in Israel? Werden Sie attackiert? Oder können Sie an Ihren Universitäten relativ unbeeinträchtigt noch Ihre Forschung und Lehre machen?
Well, it's a good question that is difficult to answer completely honest. It is difficult. It's nearly impossible to get funding to do our experimental work. And I mean, I'm pretty convinced that it is because this kind of work is not really what you want to see a result on. So it is really problematic, but I'm still having a job, so that's, in that sense, it's fine. And my colleagues, you know, just around me are, you know, we have a good relation. The university, well, I don't know how happy they are about what I'm doing, but I'm still here.
In Israel, I think the scientific political situation is much better. In Israel, we can really have free debates, and I mean, not everyone agrees with me, but I don't feel the same kind of feelings that colleagues of mine, maybe in Denmark or in other places in Europe, feel. Unfortunately, in Israel, we have real problems to worry about. So maybe that's one of the reasons. Another thing is, but I mean, the bottom line is that in Israel, I have no problem whatsoever. My university supports me. I can have, open scientific debates and so on. It is true that, getting funding is generally hard because, of the reviewing process and things like that. But maybe it's because we have a lot of sun that they don't mind me talking about the sun.
Carsten Ax. Eine Frage zur Bindung des CO2s durch Kalk in den Meeren. Lithosphäre hatten Sie angesprochen. Da ist ja das Argument der Klimachanger, dass die Versauerung der Meere durch CO2 dazu führt, dass sich eben Kalk im Meer eher löst statt bindet. Können Sie dazu was sagen? Zweite Frage ist, Sie haben von dem Zyklus mit 60 Jahren zum Beispiel gesprochen. Weiß man, woher diese Zyklen kommen? Und die dritte Frage ist, wenn Wolken zu mehr Abkühlung führen, da ist ja auch das Argument der Klimachanger, die Luftfeuchtigkeit nimmt durch die Erwärmung zu, dadurch ist mehr Wasser in der Atmosphäre, es bilden sich mehr Wolken. Dann müsste doch aber, wenn mehr Wolken in der Atmosphäre sind, eine Abkühlung stattfinden. Das ist die letzte Frage.
Okay, so the answer to the first question is, I suspect you imply, you want to talk about the over geological timescale, the past 500 million years. Where is he? On this timescale, okay, so. When we first did the correlation between the temperature and CO2 and geological timescales and found that there was no correlation whatsoever, we could actually place an upper limit, which is somewhat below 1 degree increase per CO2 doubling. But then there were a lot of people that attacked this work, and most of these attacks were totally meaningless or didn't have any teeth. But there was one argument which was interesting and raised, and that is that something that the geological or paleoclimatological community didn't consider before is the fact that ocean acidity, which is affected by CO2, affects the oxygen isotope ratio, such that the oxygen 18 is not only a proxy of temperature, but also affected by the amount of CO2. And in order to get that there is no correlation between CO2 and the temperature, it means that these two corrections have to cancel each other, and therefore the lack of a correlation corresponds actually to a sensitivity of about 1 to 1.5 degrees. I don't remember what was the second question.
What was the second one?
60 years. I didn't particularly address the 60 years or any other time scales. I don't know what are the origins of the changes of solar activity. I just, get them as a given. We can see what they were looking at cosmogenic isotopes, and we can see whether they affect the climate or not. So I didn't address, we didn't address the 60 years. And the last question was with regards to water vapor. Many of the arguments that people raise regarding the amount of water vapor and the effects of clouds are irrelevant, because in any climate model or in any change in the energy budget, whether it be CO2 or cloud cover or solar irradiance or whatever, a large effect that you have is the fact that you, say, warm the oceans, and therefore you have more water vapor in the atmosphere. So whether or not you see things like a change in the cloud cover or change in the water vapor has to do more not with what was the driver of the change, but how what are the feedbacks in the system. And this goes back to, for example, what Professor Scaffetto mentioned with the hotspot. I think the lack of a hotspot is not an indicator of what the climate driver is, but the fact that the amount of water vapor change was actually smaller, that the feedbacks that you have in the systems are smaller than what the climate models assume.
So, vielen Dank, Henrik. Vielen Dank, Nir. Also mal eine Frage an Sie jetzt, ja? Wenn man das jetzt gehört hat und nehmen wir mal an, man hat das alles verstanden, noch dazu, ja? Ja, im Ernst. Der Gedanke, dass diese Veranstaltung einen Polizeischutz bekommen hat und noch hat, ich muss sagen, es ist pervers, dass wir das brauchen, ja?